All right, so chapter 7, energy and chemical change. Energy is a very important part of chemistry. It's an important part of life, right? And it's becoming even more evident part of, well, not that it wasn't already, but as you grow up, you recognize the importance of energy consumption. People consume electricity, right? I mean, we consume energy by using electricity, but we consume energy when we eat. That's why we eat, right? We create energy. We have chemical reactions or processes or things that occur in nature that release a ton of energy. And our understanding of energy has really made a difference in the world. And our further understanding of energy will continue to make a difference in the world. So it's impossible to underestimate the importance of understanding energy. Our limitations as far as consumption of energy, production of chemicals in the atmosphere that we don't want, or waste that we don't want, are all based on our lack of understanding of energy. So there's a long ways that we have yet to go. So this is the beginning for some of you, and also for others of you, it might be a little bit of a review.
I had some stuff in high school about energy.
Okay, all right. So we'll work through this slowly. The big take-home message that we want to get from this chapter is that we're going to add on to our chemical statements. So here's a chemical reaction. That's a typical chemical reaction. This is a single replacement reaction. But we're going to add on to this little amount of chemical reaction with some information regarding the energy, with respect to the energy. And this delta H is the heat energy, and we'll talk about what that means. And the negative means that this process releases, and the kilojoules are the units of energy there. So it's releasing that much energy. It's important to recognize that this chemical reaction and this little energy tag there are linked. They're together. So this specific statement corresponds to this amount of energy. All right. And we'll talk more about that as we get closer, or as we move on through the chapter. All right. Energy is the ability to do work. We have probably in the past had conversations or heard of conversations about kinetic energy and potential energy. And kinetic energy and potential energy combined, all the energy of a system, we would call in chemistry the internal energy, or E, the internal energy. All right. Potential energy from a chemical perspective in chemistry, we call chemical energy because the energy is stored in the chemicals.
Where is it at in there?
Well, that's a good question. Where is it at? It's actually in the degree of stability of the bonds. Do you remember when we put sodium into water and we saw the big explosion in the videos?
Yeah. So
sodium explodes when you put it into water, or reacts violently, because its energy, its electrons, sodium's electrons, are held at a position which is relatively high in energy. But when sodium is allowed to interact with water or oxygen, it will be able to release those electrons and stabilize itself. And that release in electrons results in more stable products, a more stable condition, and therefore you release that energy in the form of heat. Okay? So, potential energy for chemists can be called chemical energy, because the energy is stored in how the electrons are interacting with the nucleus, or how one atom's electrons are interacting with another atom's electrons, and we call that a bond, right? So for example, if I have an oxygen atom here and an oxygen atom here, and I show some electrons around maybe the nucleus of the oxygen atom. Let's start over. I'll just draw a nucleus instead. There we go. We have a nucleus. It's an oxygen atom, and there are some electrons. And if I have another nucleus here, another oxygen atom with some more electrons, right? as I bring these atoms together, then the electrons can begin to share share its density with the other nucleus. And this results in what we call a bond, and you probably already have heard of bonds and understand what that means to a degree. Two elements bond together because they're sharing electron density. This sharing of electron density also stabilizes the electrons, stabilizes the elements, and the resulting molecule or compound or grouping is more stable than the individual atoms. So, we can think of each one of these bonds as kind of a spring. And the more stable the bond is, the closer and slower the vibrations are. But if the bond is unstable, those atoms bounce violently back and forth, those two nuclei bounce back and forth very violently, and they're prone to be disrupted by the approaching of another atom or another electron, right? Because if another electron comes that can share electron density, then that stretching can break easy, and one atom or nucleus can go off with another electron, right? So in this way, that is where our energy is stored, in those bonds. And you can think of those bonds as springs. The more stable ones are slower and closer, but the less stable bonds are farther away from each other, and they are moving more quickly. Okay, now, or they have more energy, because sometimes it depends on the mass of the nuclei, right? Let's think about this scenario. Here's a nucleus over here, okay? And here are some electrons. And here's another atom over here, nucleus, and some more electrons, okay? If these two atoms are separate from each other, they're away from each other, the electrons can't interact with the neighboring nuclei, all right? If this is the case, if you bring these two atoms close together, then the nuclei can begin to interact with the neighboring electrons. And if, and only if, this results in stability of some kind. So if the nuclei, both of these nucleuses, if they want to have more electron density, then bringing them closer will allow them to kind of reach out and get a little more electron density, then a degree of stability can be found. And then a bond will result. But simply by forcing them together doesn't mean a bond will result. Bringing two atoms together will only result in a bond if that proximity actually stabilizes the resulting condition. Okay? And because of this, it always takes energy to break a bond. And forming a bond always releases energy. Forming a bond always releases energy. Now, recognize that I said forming a bond releases energy, not bringing two atoms close to each other. That won't release energy necessarily. Only if the two atoms can actually form a bond, which means utilize each other's neighboring electron density in some way. I mean, for sodium and chlorine, right? We talked about that before. That's an example where sodium atoms and chlorine atoms actually, sodium does what? Do you remember what sodium does?
It gives an electron to chlorine.
That's right. It completely transfers an electron to chlorine. And so that results in stability. Okay? So unless there's a reason that the added amount of electron density will stabilize the system, just the proximity itself will not create a bond. And because of that, you can always say that breaking bonds, no matter what kind of bonds they are, will always require energy. Forming bonds, no matter what kind of bonds they are, will always release energy. Okay? Now, you'll hear contradicting statements in different classes with respect to this forming of bonds and breaking of bonds. People say, it's a high energy bond, we break that high energy bond and we release energy. That's not a complete statement. It's out of context. So what they're really missing is just the part that says there's a high energy bond, that bond is broken and allowed to form a more stable bond. And so energy is released. All right. They don't talk about that bond forming somewhere else. They just say the high energy bond is broken, therefore energy is released. Okay. But the breaking of any bond will require energy. The forming of any bond will release energy. Okay. Good.